Thanks very much for the invitation. It's a real pleasure to be here, and it's great to have Nathan kick us off with such a great first talk. Yeah, so I'm going to talk to you about rank for this mini course. So what's rank? The definition, the rank of a group is just the minimal size of a generating set. So this is maybe one of the easiest to define invariants of of an infinite group that say. And but I guess what I'll try to convince you of today, and also in the next two lectures, is that, well, it's actually pretty hard to study. But before we get to the difficulty, let's try to make ourselves feel better by computing some easy examples. So maybe the first example to talk about is, so I could take the rank of just z to the n, and that is, no surprise, n. Okay, but just sort of let you know what's involved in these computations of rank. Well, okay, usually an upper bound is easier, because then I just have to give you a generating set, and so like the standard basis elements generate, and there are n of them, so that's the upper bound. But then even for z to the n, like the lower bound is not completely trivial, right? You have to use like linear algebra. So I mean, the point here is that like any generating set for z to the n spans Rn. So it has at least n elements in it, because Rn has a dimension n. Okay, so I'm like leveraging linear algebra to prove this just group theoretic fact here. All right, so that's maybe the first example. Maybe a first basic property is that if G surjects onto H, so this means this is a surjective group homomorphism, then rank of H is at most rank of G. Okay, and that's just because if you have a generating set for G, you project it onto H and it generates H. Yeah, but we can use this together with the Zn example to get a couple more examples. So for instance, what about the free group? If I take a free group on n letters, then the rank of that is n. Okay, and again, like the upper bound is obvious because it's generated, it's defined to be generated by n elements. And then for the lower bound, you just note that if you take the free group, then that surjects onto its abelianization, okay, which is Zn. And we already computed that Zn can't be generated by less than n elements. Yeah, interrupt me with questions, please. All right, so that's one example. So maybe for a second similar example, we could do the rank of a surface group. Right. So if I take so sigma G here is going to be a closed surface of genus G. Okay, and the rank of this is 2G. And why is that? Well, it's easy to generate the surface group by 2G loops. I just sort of add two loops that for each hole I add two loops, and that gives me a generating set. Maybe there's more genus, and then I add loops around those too. So this is sort of the proof of the upper bound, and then for the lower bound, you again say that the abelianization is z to the 2g. Right, so like pi1 of sigma g surjects, say, onto the abelianization, which is first homology, and that's z to the 2g. All right, so this is sort of all the easy examples that I'm going to give you. So maybe for a first non-trivial result, we have Grushko's theorem, and so this says that if A and B are groups, then you can look at the rank of the free product of A and B, and that's the rank of A plus the rank of B. And so maybe this should not be too surprising. You know, if you take a free product, then the elements of A and B are interacting as little as possible in the free product group. And so, you know, you should expect not to be able to generate this more efficiently than by using a generating set for A and generating set for B. Okay. But you know, the theorem is not, you know, it's not so obvious. Yeah, and maybe let me just say, like, what's a corollary of this? So as a corollary, you get that if G is finally generated, then you can write G as a free product of you know, a bunch of groups A1 through AN, where no AI is itself a free product. Okay, because what's the point? Well, yeah, or what's interesting in this statement here? Well, so you start with some G and then you wonder, okay, well, let me split that. Maybe that splits as a free product. If it does, split it. You look at the two factors and you maybe those split like two free products, and then you split. And so you need somehow to say that this process terminates. And the reason it terminates is because of this Gruschius theorem, okay? Because the rank of the pieces has to be decreasing. And this should, you know, because Nathan just talked. So this statement is sort of a group theoretic analog of something in three manifold topology, right? So remember Nathan just talked about these prime decompositions of three manifolds and mentioned how if you take a three manifold and you split it up as a connect sum, then the fundamental group is a free product. I mean, this is sort of a group theoretic analog of that then. You know, saying you can take your group and split it up into freely decomposable pieces. So maybe for one more thing that we can actually prove. So let's talk for a minute about rank, about how rank behaves when you pass the finite index subgroups, because this will come up later as well. Yeah. Yeah, I mean, right. I think you should not expect it to be a random group that I give you to be a free product. Yeah. Mm-hmm. Yeah, I mean, in some sense, like, right. I mean, what is this corollary sort of allowing you to do? It's allowing you to say, like, okay, if I want to study group theory, then this corollary sort of reduces the study of group theory to the theory of things that aren't free products, right? So, yeah, what's up? Yeah, I mean, there is a uniqueness statement in general. Yeah. Mm-hmm. Yeah. For finally generated groups, right? If I have a finally generated group, then like the isomorphism classes of these groups are all unique. All right, so let's talk about finite index subgroups for a second. So the fact that is that if H in G has index n or index m, say, then I claim that the so I want to say like how rank can change between G and H, and in order to formulate this, it's better actually to talk about not rank but rank -1. Okay, and the theorem is that so rank of H -1 is at most m times rank of G -1. Okay, and what we'll see in a second is that this is sort of like an Euler characteristic statement, and I think this is a really nice thing to prove. So let's just prove it. Okay, so proof. All right, so let's let like xg be like a 2 complex with pi1 of xg equal to g. Okay, and where the one skeleton is you know, a wedge of rank G loops. Okay, so right, so I take like a minimal generating set for G, and I you know, I make a wedge of that many loops, and then I can make a complex with fundamental group G by adding a whole bunch of 2 cells to that, corresponding to relators. I mean, maybe infinitely many 2 cells, that's fine. And then what do you do? Well, the sort of crucial observation here is that if I look at rank G minus 1, what's that? That's like the negative Euler characteristic of the one skeleton of XG. Okay. Right, XG is like this wedge of rank G loops, and so the Euler characteristic is 1 minus rank G. Okay, and then what we do, we just let maybe XH going to XG be the cover corresponding to H. Okay, and then we can we derive the formula by saying that if I look at rank H minus 1, okay, so what's that? Well, I can look at the one skeleton of this cover, and so this I don't know that the one skeleton of this cover like the loop, I don't know that the loops in this one skeleton of the cover generate H efficiently. Okay, all I know is that they do generate H, and so I get an inequality here between the rank of H minus 1 and the rank of the pi 1 of the one skeleton. But then I can do the sort of same thing. So this is this is again like minus Euler characteristic of this one skeleton. Okay, and then we know how Euler characteristic changes under covers; it multiplies, and so then you get m times the Euler characteristic of the one skeleton of XG, and that's exactly m times rank G minus 1. Okay, so far I've been all optimism. If yeah, and actually, wait, one more thing about the facts. So maybe just a quick remark. If G is free, this is an inequality. Okay, and just the point is that because there are no, if G is free, then there are no two cells anywhere, and then you actually get an equality in this step. Okay. Yeah, but so far I've been all optimism, and I've been giving you a whole bunch of positive results here. So just to convince you that things are not quite as easy as they might seem, let's look at the following example. So what happens if you take a direct product of groups? Oh no. Oh my God, it doesn't work. Yeah, right. So let's let BS12 be the Baumslag-Salentar group. So this is generated by A and T, where PAT inverse is equal to like A squared. Okay, and let's let okay. Well, what's the rank of this, by the way? 2. Okay, this has rank 2. Right. So this has why does it have rank 2? Was that? Or, say it again. Sorry. I mean, easier than that, right? Yeah, right. It has rank 2. It has rank 2. Like the upper bound is obvious because there are 2 generators above. And then what about the lower bound? It's not cyclic because it's not abelian. Okay. Right. So it's not abelian and hence not cyclic. Great. So still everything is fine, right? But then the weird claim is okay. So let's let G be equal to BS12, and I said direct products. Let's do the easiest direct product possible, Z. Okay. Right. So what's the rank of this group? Okay. Well, I know it's at most 3, right? And you sort of expect it to be 3 because, right? But actually, rank G is 2. Right, and it's a super easy proof. Like, how do we prove it? So what's a presentation for G? I can do ATS, where again, I have the same Baum-Slack-Solitar relation. And then also this S is central. Sorry. AS ST is 1. Okay, and so then I claim that if I look at the elements AS and T, then they generate. And why is that? It's because if you take, so look what happens if you take, if you conjugate AS by T, okay? So if I conjugate AS by T, then the T commutes with the S, right? And so you get TAT inverse S, which is A squared S. But the sort of trick here is that if I look at AS and A squared S, then they generate the whole subgroup generated by A and S. And why is that? Well, what's okay, so here's why. The subgroup generated by A and S is what? It's Z squared because A and S commute. Okay. And then inside of Z squared, what are these elements? These elements are like the vectors 1, 1 and 2, 1. And those generate Z squared. Yeah.
Silly question, but why go to all that? Why not put specific something to like finite groups?
Yeah, that's a great question. That's a great question. Yeah, I guess you could do that too. That's awesome. I like this one better for some reason. Right. So like, because this is right. That's awesome. Right. So if I do like Z mod 3Z times Z mod 5Z, then that's also rank like rank 1 because it's cyclic again, right? Yeah.
So our finally generated group exists finally generated group G such that G is isomorphic to G product G. Well,
yeah. Right. Cool. So all right. So let's continue. So direct products are badly behaved because of the cyclic group example or because of this example. So yeah, what else? Yeah, so maybe I'll just make a couple of remarks on algorithmic questions. So just for Mark, so first, there does not exist an algorithm to calculate the rank of a group, say, from a finite presentation. Okay, and this, if you know anything about algorithmic problems in group theory, then this is not a surprise, because really there's this theorem of Adian and Raban, well, and also Raban from like the 50s that says that there's no algorithm to check whether a group's trivial. And what's trivial is the same as having rank 0. Yeah. Yeah, so that's a great question. Also, there doesn't exist an algorithm even for hyperbolic groups. Algorithm even for hyperbolic groups, and that's sort of more surprising, because most of the other algorithmic questions that you can come up with for hyperbolic groups are solvable. Yeah.
Algorithm for the rank or to decide?
For the rank, for the that computes the rank. Yeah, right. You can tell when a group is trivial. Okay, so yeah, and I guess this sort of comes down from maybe I'll just mention this is kind of a corollary of something called the Rips construction, and you can read more about that in the homework problems that we'll have later if you want to. Yeah. So okay, so maybe we're starting to get the picture that rank is a little bit more complicated than we realized. So now this is supposed to be like a conference on 3 manifolds. So let me bring 3 manifolds into the picture. So okay, so let's let M be a closed orientable 3 manifold. And so from now on, whenever I write rank M, that's rank pi1 of M. And so it turns out that the rank of a 3 manifold is related in sort of mysterious ways to another invariant of 3 manifolds called the Heegaard genus. So I'm going to tell you what that is for a little bit now. Yeah, what's up? Yeah, right. If you want to figure out like the rank of any of a genus G surface is 2G, and so you're asking like how it multiplies under covers, and so like the Euler characteristic of a surface multiplies under covers, and that's almost the same as the rank. So the rank is like almost multiplicative. Yeah. So okay, so let me tell you what Heegaard genus is. Okay, first let me tell you what a handle body is. So a handle body, so maybe a genus G handle body. Well, it's just okay. Let me say it the sort of silly way. It's a filled-in surface in R3, filled-in genus G surface in R3. Okay, so it's the 3 manifold that you get by just taking a genus G surface sitting in R3 in the way that you picture it in your heart, and then you fill in the inside. Okay, so 3 manifold with boundary. So you can think about it that way. Okay. So yeah, so I can think about it that way, but you can also think about it. So it's sometimes useful to note that alternatively, handle bodies of like whatever genus are they're created by by taking like 3-dimensional thickenings of graphs, of finite graphs. Okay, so it's like if I give you some finite graph like this or something, then you can imagine thickening it by replacing each of the vertices with a little 3 ball, and then each of the edges with a like a disk across an interval. And then that gives you something that looks like like that in this picture. And this is again like filled in. No, I mean, I guess what I'm trying to indicate here is that like you can do this with any finite graph. So I mean, you can do it with, right? I mean, yeah, if you just take like a wedge of G loops or something, and then take and thickening of that, then you'll get a genus G handle body. But any finite graph gives you a genus G, or gives you some genus handle body. Any other questions so far? So then, okay, so let's try to define this Heegaard genus. Well, so definition: a Heegaard surface in M is an embedded surface that cuts M into 2 handle bodies. Right. So I have a embedded surface, has 2 sides, and each one of those sides is a handle body. Okay, and we sometimes, there's sort of multiple ways to talk about these, and we sometimes say that well, we say that this decomposition is called a Heegaard splitting. So we say that this decomposition is a Heegaard splitting. All right, and then what you can do is you can say, well, okay, so there's this basic fact of 3 manifold topology, which is that every M as above admits a Heegaard splitting. Okay, and I don't know, you can prove this in many ways. Sort of the easiest way, maybe from first principles, is via Morse theory. But if you're willing to accept that M admits a triangulation, then you can sort of visualize a Heegaard splitting. So you triangulate M, and then you can let you're looking for 2 handle bodies inside of M that share a boundary, and one handle body is going to be like a thickening of the one skeleton. So H1 be a thickening of the one skeleton of the triangulation. Okay, and remember we said that thickenings of graphs give you handle bodies. And then you can, the sort of interesting thing is that you can let H2 be a thickening of the dual graph. So, right, so I mean the picture, well, I'll just sort of draw a box like that's a proof, but the point is that, okay, here's your triangulation. You're supposed to thicken up these edges a little bit, and then the dual graph looks something like, do I have colors? Oh, you brought your own colors? Oh, really? Thank you. Yeah. So the dual graph looks something like this. Well, okay. Okay, and then you can sort of try to convince yourself that if you thicken that up, then that gives you something that's, you know, like, well, as you thicken up both the one skeleton of the triangulation and simultaneously this dual graph, then you get two handle bodies whose boundaries eventually sort of collide, and then you get this Heegaard splitting. All right, so yeah. Yeah, there is. So the point is that instead of looking for two handle bodies, so you want a surface that like splits it into two what are called compression bodies. Yeah, which is sort of like yeah, it's like in the R3 picture, you take a surface in R3 and then you fill in part of it, like fill in the right half. Yeah. So yeah. Okay, so then, well, so if every M admits a Heegaard splitting, yeah, what's up? Yeah, I mean, I guess you need to, right, you need to use I made this assumption on M that it was orientable at the beginning. And that's, I guess if you, yeah. Okay. So, yeah. Okay, so every M admits a Heegaard splitting. And so then that allows us to define the Heegaard genus. As a so I'll write G of M, and this is like just the minimal genus of a Heegaard splitting. Right, and what's, yeah.
Let's give an estimate on the top to the Heegaard genus.
Yeah.
Is this evenly
Yeah. Yeah, I mean usually the Heegaard splittings that are produced from this fact, from the proof of this fact, are terrible. Like they use way more genus than you would ever want. Yeah, like in particular, I guess if you have a triangulation of M, then you can, right, you can use that to like bound the volume of if it's hyperbolic, you can use it to bound the volume, but you know, you can produce a wealth of hyperbolic manifolds with Heegaard genus 2 that have like volume going to infinity. And so, I mean, yeah, these are usually terrible in terms of the Heegaard genus. Yeah, the answer is like there are manifolds where there's the number of tetrahedra in the triangulation goes to infinity, but the Heegaard genus is always 2.
Oh, okay.
Yeah.
For the best triangle.
Yeah, for the best triangulation, right?
There's only finite many things you can build out of 100 tetrahedra.
Yeah, right.
Okay.
Yeah. Yeah, right. That's a better answer than talking about volume. Yeah. Cool. So, all right. So I said that this had something to do with rank, right? So what does it have to do with rank? Well, maybe fact. So I claim that the rank of M is always at most the genus. So why is this? Well, the point is just that if you write M as like one handle body unioned over this Heegaard surface S with another handle body, then if you look at pi1 of H1, say, then this surjects onto pi1 of M. Okay. And the reason for this is just that well, why? So I mean, so any loop in M that's sort of like based in H1, can be, well, you can sort of perturb it off of like a spine for H2 and then just homotop it into to H1. So what do I mean by that? So I mean, like, here's a picture of H2, and then you know, I can draw like a graph. Let's inside of H2. Let's call this the spine of H2. And if I have a loop based in H1, then maybe it has some parts that sort of go into you know, into H2. And so you can perturb it so sort of off the spine of H2, and then sort of just homotope it back into H1. Okay, and the point is just that, like, if you take this spine and you remove it from H2, then you get something that's just a product of the surface and like a half open interval. And so then I can you know, take this arc that goes into H2 and just like push it to the boundary and push it back into H1. What's up? You can miss the spine just because of like dimension considerations. Like you know, the spine is one-dimensional. This loop is one-dimensional, and so I can just sort of like, you know, perturb it off, and now it's now it misses the spine. What's up? I mean, you know, you know, you can homotop you can homotop anything to be smooth, say by smooth approximation, and then like homotop it off the spine. Ah, excellent. Right. Yeah. Right. This is like, right, if you're in a differential topology class, right, this is how you prove the sphere is simply connected, right? You take a potentially space filling curve and then you perturb it. Right. Anyway. So okay, so rank is at most genus. And then okay, so then, you know, what's the natural question to ask if somebody writes that on the board, like, are they equal? And in fact, this was a question of Waldhausen from the 1960s. And so he asked, are they equal? And maybe let me just first convince you that this is kind of a hard question. So why is this hard? Well, here's a special case. So if I'm asking if they're always equal, then one thing I want to prove is I could look at the case where rank is 0. If they're always equal, then that should imply that the Heegaard genus is 0, right? Okay, so this is our question. But then what do these things mean? Like okay, rank 0. That means that M is simply connected. Great. So what's Heegaard genus 0 mean? That means that M is like 2 balls. So a genus 0 handle body is a ball. So then M is 2 balls glued together along their boundary. But the only manifold that you can make by gluing 2 balls along their boundary is a 3-sphere. And okay, so right, and so then this arrow on the right is the Poincare conjecture. And so here, star is the Poincare conjecture, which was you know, proved in 2003 by Perelman. You know, in hundreds of pages, counting all the work that went into it. Right. So, okay, so that's just like the trivial case of the rank versus genus question. Okay. Yeah. So okay, but now we know that the Poincare conjecture is true. So okay, so now we can ask whether the rank versus genus question is true in general. And it turns out the answer is no. So the answer to the question is no. And the first examples were due to Boileau and Zishang in when? 84. Okay, and so So they produced like ciphered hybrid manifolds. You know what those are? Where the rank is 2 and the Heegaard genus is 3. What? So they're. I think they're like the orbifold is like a sphere with 3 cone points, I believe, of like some particular orders. So what's that mean? SL2R? Yeah, right. What's that? I think not. Not. I think. Yeah. Right. Yeah. Right. I think the point is that like what paper, they basically try to calculate like all the ranks in Heegaard genus with low low complexity fiber spaces at least. I think they show the mostly the with the ranks always the ranks are the same and they're the same, but then there are these 2 examples. I think let them remembering they've been correct. I thought they were with 3 cone points, but yeah. What's that? Yeah, I don't know. Maybe I don't know. Yeah. No, I mean it's all good. Yeah. Yeah. Also not really. I welcome your input. All right. So right. So then there are also some further examples that are given by Schultz and 7. So further examples. I'll just leave it at that for now. So these were still not hyperbolic. And so a lot of hyperbolic geometries in particular were unsatisfied by these examples, and they're like, hey, is there a hyperbolic 3 manifold where the ranks not the genus? And that was a topic of a lot of interest for a few years until finally Atelier in 2013 showed that there are still examples. So they're just hyperbolic such that the rank is less than the genus. And maybe I should also say that in both of these cases, like they also show that the difference between rank and genus can be made arbitrarily large. Okay, so also genus minus rank can be arbitrarily large.
Is this like a statement that if they're not equal, then you can make them arbitrarily large, or just these particular examples?
Well, I mean, I guess you could take like these examples and then take a whole bunch of connect sums of them. But I guess the point of these examples are that they produce prime 3 manifolds where the difference can be arbitrarily large, and also here like you can't do like connected sums with hyperbolic manifolds, and so there's content to say that the genus minus the rank can be made arbitrarily large. Say again? I guess it's not like right. If you have rank 1, so you're I mean you can say what are all those those manifolds, I guess, and right, and they all have the right Heegaard genus. Like you're like a lens space, say, and then the Heegaard genus is 1 as well. So yeah, but in some sense, like this is kind of like this is kind of the state of the art as far as well, I'll say some more stuff in a little bit, but sort of there are not a lot more examples than these. And so maybe let me just state a couple open questions about this. So maybe first, okay, I can make the genus minus the rank arbitrarily large. Can I make the ratio between them arbitrarily large? Right, so are there, well, maybe I'll phrase it like this. Are there Mn where like the rank of Mn over the genus of Mn goes to 0? So we don't know. I think actually the smallest ratio that's known here, I think, is like 2/3. Okay. And second, like, is a right, is you could look at the Heegaard genus of a manifold, and you could ask, is that at most f of rank m for any f? Okay, so I mean, said a different way, this question is asking, like, can you have a sequence of manifolds with like with rank 2 and where the Heegaard genus goes to infinity? Okay, yeah, and yeah, I think even that is unknown. Right, and so this is sort of all kind of wide open. I'm supposed to go to noon. Yeah. Okay. Cool. All right. So I think what I'll do, like, these two questions will sort of occupy, in some sense, the entire rest of the mini course. And I'm going to spend maybe the next 10 minutes and also some of next time talking about the first question, and then we'll sort of talk about things related to the last question and also some other stuff. So, okay, but what about this ratio? So it'll be convenient to sort of recast this question a little bit, where instead of talking about the ratio between rank and genus, I talk about the ratios of both of them individually with something like the volume of Mn, if if Mn is hyperbolic, say. And really, it's actually, I think really what we'll do is we'll look at sequences Mn that come from successive covers of a given 3 manifold, and then compare both of these to like the index of the degree of the cover. And so maybe let me start more generally with like a just purely group theoretic notion. So this is maybe this can be called rank and Heegaard gradient. So okay, so let's let gamma be a finitely generated group, and let's let gamma n be a sort of a chain of finite index subgroups. So all I just mean is that these are all finite index, and it forms a chain, which means that gamma contains, like, gamma 1 contains gamma 2, et cetera, et cetera. Okay. Right now, I'm not assuming anything else about these subgroups. All right, so then I can define the rank gradient of this gamma of this. Okay, maybe I'll write it with 2 sets of parentheses just for clarity the first time. So this is called the rank gradient. And what's the rank gradient? Well, you take just the rank of gamma n, and then I'm going to subtract 1, and then you compare that to the index, and then you take a limit as n goes to infinity. And so why do we? Okay, if these indices are going to infinity, then like the -1 doesn't really matter. So you can basically pretend that this is just rank on the top. But why do we include the 1? We include the 1 because of this fact that I proved to you earlier, which implies that this sequence here is monotone decreasing. Okay, so the fact that if I take like rank h -1, then that's at most like the index of h and g times rank of g -1 that we proved earlier, implies that this sequence is monotone decreasing, and so that you can just, well, and in particular the limit exists. So that's rank gradient. Yeah, so.
Is there any inequality like one for rank for the genus, for the Heegaard genus?
Say again, or?
Like the inequality that you have for rank, is there a similar thing for the Heegaard genus?
Yeah, there is a similar thing. So right, so we'll right, we can put a similar notion of Heegaard gradient up on the board in a second, and then also that will be monotone decreasing for the same reason. Yeah. And so you can do a lot of examples here, like I don't know, what are some sort of very quick examples? So you could look in Z or something, then like what's the rank gradient of the subgroups NZ, or I guess this is not a chain, right? So what do I like to the NZ? So now it's a chain. Okay, so what's the rank gradient? Well, the thing is, these are all cyclic, so the rank is always 1, and so you're defining by bigger and bigger indices, and so you get 0. What's up? Oh yeah, yeah, right. Right. Okay. So if I do z squared, then I actually get a sequence that converges non-trivially to 0. Okay. Great. So yeah, and then also in Fn, any chain, or like how about Fk, any chain, gamma n has a rank gradient equal to, well, we said that in a free group, rank actually, like this is actually an equality here, right? And so then what does that mean? So that means the rank gradient's always what, k? Is that right? Yeah. K minus 1, right? All right, so that's rank gradient. And so then you can, if your gamma happens to be a 3-manifold group, then you can talk about Heegaard gradient. All right, so if gamma equals pi 1 of m, m closed, say, orientable 3-manifold, then right, so then we can define well, okay, so then if gamma n is a chain, we can construct the a tower of covers. So you start out with m, and then that's covered by m1, covered by m2, covered by ... where pi 1 of mn is gamma n. Okay. And then we can define the Heegaard gradient. So the Heegaard gradient of like the sequence mn or the subgroups gamma n. So this is what? This is a so you want to do the same thing. Limit n goes to infinity. That's the Heegaard gradient. And then okay, so similarly, just as we didn't put rank on the top, we put rank -1. It's convenient. I don't know, if you want this sequence to be monotone decreasing, you don't put genus on the top, you do like the Euler characteristic on the top. So you do, or the negative Euler characteristic. So I do like 2 times the g of m times g of m minus 2. And then divide that again by the, or sorry, g of mn.
Question.
Yeah, what's up?
Stop showing.
What does it? Does that mean ln of natural log of z, or
I
goes
don't
to?
know how to. Yeah, I don't. It's L-N. Well, yeah, I don't know how to start.
Yeah, I don't know. I'm not sure what that means, but I'm happy to answer the question afterwards, though, if you want. Yeah,
Yep.
I mean, which only a few minutes. Okay, so here you just do this Euler characteristic over the index, which is the same as the degree of the cover. Okay, and then right, so maybe homework. So this is the sequence is monotone decreasing. So the limit exists. Yeah, and so then what's the right? What's a question? What's a reformulation of like some of the questions I was asking about rank versus genus before? So how about this question? Is there a sequence, or is there a tower of covers where say the rank gradient, and maybe I'll sort of go back and forth between writing like gamma n and mn, but the subgroups correspond to the manifolds. And so is there a tower of covers where the rank gradient's 0, but the Heegaard gradient is not 0? And this is this is open. Yeah, so maybe I'll stop there for today, and we'll spend some more time next time talking about this.
Do we have any questions for you? Is there a direct relationship between volume and rank for the hyperbolic?
No. Yeah, you can. Yeah, I mean, you can have you can have manifolds with rank 2 where the volume is like as big as you want. If you bound the volume from above, then you'll get a bound on, then you can get a bound on rank from that. It's going to be a really bad, really bad bound. Yeah.
The examples, the hyperbolic examples with arbitrary arrangement, gaps. Do you know if one can pass to a finite cover where the gap becomes smaller?
Wait, sorry. Say what about the gaps, or?
The examples where the rank and the
Oh, where the difference is big?
is big.
Hmm.
Is that stable in passing to finite covers? Finite index.
Do you mean like did those examples come from like come from covers, or?
If the gap can become smaller when you pass the finite index. So good,
Yeah.
In Calvin's example,
Mhm.
does the discrepancy between rank and genus disappear as you pass to covers?
I mean, probably you can pass to appropriate finite covers where it disappears. Yeah, I mean, probably. Right, I would imagine it would like depend on the cover. Yeah. I don't know.
Yeah. That feeling like the last question.
I mean, I kind of don't think that I should be so bold as to have a gut feeling about it. 'Cause no, I mean, yeah, no, I mean, I don't know. No, I think is the right answer. Yeah, we'll see next time. That I mean, this is like super subtle and has to do with like one thing that I'll talk about next time is like how this there's some work of Abert-Nikolov that relates this question to like one of the big outstanding open questions in measurable group theory. So like, I mean, yeah, I'm not really sure what to expect.
Is the rank as known for fiber hyperbolic manifold?
No, yeah, I think even in that case, it's not known. Yeah, it's a good question.
Maybe actually comment on Maddie's question.
Yeah.
Via the magic of virtual fibering, I think you can answer Macarena's question, which is you pass to a cover that's fiber, then you pass to a cover that has giant translation length.
Yeah, that's a good
And
point.
that's why I did yours with Juan.
Yeah. Yeah, that's a good point.
There is a finite cover.
Mhm.
Where
Yeah.
So you mentioned algorithmic things earlier. Is there an algorithm to keep the rank and the Heegaard genus for the three manifold?
Yeah, right. That's a great question. So, right, I think there's no algorithm known to compute the rank. Well, let's see if I get all this correct. I think there is an algorithm to compute Heegaard genus of a three manifold. I think this is a Atelier. There's no algorithm known to compute the rank of an arbitrary three manifold. There is an algorithm to compute rank of hyperbolic three manifolds, though. This is a Kapovich-Weidman. Yeah, so right, there's still some subtlety there.
So I think like the way you phrased your talk, we were motivated by the rank of a group, and then you brought up the Heegaard genus as a way to hopefully let us understand the rank of a group. Is it clear that the latter is easier to understand, like the Heegaard genus? Is it always easier to understand? Like
Yeah. I mean, I sort of feel like I'm dismissing the field of Heegaard splittings when I say that, but yeah, I think it is easier to understand because you have a lot more to start. You have a lot more to start with, right? Like when you start with a Heegaard surface, then you can immediately start doing geometry from that. Geometry and topology. You can start doing things like trying to find, maybe trying to make this, if you're in a hyperbolic manifold, like trying to make this Heegaard surface minimal if you can. And then you can, say things about how Heegaard genus relates to the geometry of the manifold from that. But it's harder, it's kind of harder to do that with rank. Like part of the point of like at least the last talk is going to be about, well, how do you view rank geometrically? But you know, it's not as, yeah, it's harder to get as much out of that. So there are a lot of like basically all maybe all theorems about rank were known previously for Heegaard splittings. Well, maybe not quite, but yeah.
Thanks.
Mhm.
There are no further questions?
Matt?
I thought I said something on the
Okay, what's the, besides like the studies of Darwin with the Nikolov, idea of how the learning behaves, so the foregoing units, what is the, is there any other motivation?
Like, why did people study the? Yeah, well, I mean, I think, oh, you know, I forgot to, okay, I forgot to even put Mark Lackenby's name on up on the board, but let me say that both of these notions, I think, were first formulated by Mark Lackenby, like rank gradient and Heegaard gradient. And I think his motivation was that there's some, you know, there was a plan that he had for solving this three-manifold conjecture called the virtual Hawken conjecture, which was, you know, later solved via completely different means by, you know, Ian Nagel using lots of work of Donny. And so I think like that in particular, you know, he was first motivated to look at these things from that perspective, and then also from just the rank versus genus perspective. And I think that's where it first came from. And then since then, now there's you know, this work that maybe you're more familiar with like, you know, interpreting rank gradient versus cost and such. Yeah. Yeah, right.